Hello everybody, my name is Anthony Chido and I'm a senior civil engineer in BOMO. I work in the TSMO arterials and planning section, more specifically in the traffic signal unit. Today I'm going to be presenting on trends in traffic signal maintenance. This mainly covers a project that we did back in fall of 2019 with Michael Baker. And the main point of the project was to streamline our traffic signal maintenance agreements, as well as update some of our traffic signal maintenance publications. This slide here gives a high-level overview of the project and the goals that we wish to accomplish with it. The first one was to update our maintenance publications. So this includes publication 191 for those of you that are familiar with it. We also wanted to improve the current traffic signal maintenance agreement process. This involved working with municipalities and also consultants and getting a lot of feedback to see what the current process was, how the districts are doing it, and just making sure that we could streamline it to make it a quicker, easier process for all of our municipalities and districts. We also wanted to make sure, as a part of this project and making sure that information was correct, that we verified traffic signals are operating per their permit. This is important because our permits designate signal timings, where equipment should be, and when all this is in place correctly, it ensures that the traveling public gets to where it needs to go safely in an effective manner. So making sure that all that's in line is very important to us. We also want to encourage our municipalities to do preventative maintenance on their equipment. This is a big step because even though it may be more of an upfront cost, it's important because in the long run, the municipality would probably see savings, especially in cases where if say a traffic pole is neglected for a while and there's a catastrophic failure, that could lead to some pretty high costs and delays in traffic. That was some preventive maintenance. It could have been spotted earlier or fixed or replaced at an earlier time before any failure occurs. We also wanted to clearly define what the responsibilities were between districts and municipalities when it came to updating data in TSAMs, updating permit information, so on and so forth at all of our intersections. And we also wanted to be aware of what kind of equipment there is currently in Pennsylvania at intersections, what kind of controllers are being used, what kind of detection is being used. All this information is very important to us in a central office standpoint. It helps us determine life cycle evaluations for different products, helps us become technical experts so that we can properly assist districts and municipalities whenever they come to us with questions concerning different products. So having all this data stored in TSAMs and making municipalities and districts aware of it really helps us from a central office standpoint, as well as gives all that data and information to their respective users as well. So that's very important. It was a big part of this project as well. This slide here is a graphic overview of the goals that I went over in the last slide. It kind of shows what corresponds to what in terms of different parts of the project. So you can see when it comes to clarifying roles and responsibilities, these would be defined in our TSAM's policy. At this point in time, when we were doing the project, this was an interim policy. So that's why there's a dash line leading to Pub 191 revisions. So the immediate course of action was a TSAM's policy that would eventually be incorporated into Pub 191. This also includes changes and updates to the TE 160 form, which is what municipalities submit to districts whenever they want to construct a new signal or make modifications to a current one. And that's the main point in the streamlining of the signal agreement process, is the TE 160 that was revised down to one page and also would not require a municipal resolution moving forward, but we'll go on further into that in a future slide. Another part of this project, and this is always an ongoing effort of ours in the traffic signal unit, is increasing TSAM's user friendliness. I realize I may have neglected to say what TSAM's stands for in a previous slide. TSAM's is our traffic signal asset management system, and we use that. It's a free site software for municipalities and for us to store traffic signal information, whether it be projects, specific intersection information, permits, anything traffic signal related should be found in TSAMs. And as part of this process, we also created TSAMs help documents and also a guest user access for TSAMs. TSAMs is based on the ECMS security frame set. So getting access to that sometimes can be a little lengthy or a little difficult. So as part of this project, or what was incorporated was a guest user access that allows mostly for contractors to input updates to intersections in TSAMs, which are then data verified by the districts and the district staff, and then it's added to the live TSAMs database at that point. But that was another part of this project as well. The first thing that we did with this project was the TSAM survey. This went out pretty much right at the beginning, as I stated, fall of 2019. We sent this to municipal signal contacts, contractors, consultants. We sent it roughly to about 300 individuals. Some of the facts below are listed, what we found out from the survey. 81% of our municipalities use signal contractors for their maintenance. This is important because, as it turns out from that means a lot of contractors would be using TSAMs when they're making TSAMs updates. So getting that guest access was important as part of that. One fact that really surprised me was that 75% of municipalities still use paper records when it comes to their traffic signals. In a time where people are working from home a lot, in a time where digital signatures are becoming a thing, having paper records still, this was probably the biggest shocker to me, to be honest with you. And we also learned that about 22% of municipalities have tried to implement TSAMs into their daily operations. Number's a little low. We'd like to see that a little higher, but as part of this project, increasing awareness of TSAMs and making sure that people are aware of what it can do, I think that we tried to get that number up as well. So the new traffic signal maintenance agreement process, and I know what you might be thinking, that's not a typo up top. TSMA is not a typo for TSAMs. TSMA is the acronym for Traffic Signal Maintenance Agreements. The new process that we came up with during this project was for municipalities. They would have to go through one more agreement with the state, or we have them go sign into a new agreement with us. In this new agreement, the municipality would designate a position within the municipality, whether it be the head of a road crew or whether it be the director of public works. Whatever position is most relevant for each municipality, they would designate as someone to approve their signal permits and to sign off on the TE 160s. And then from there, once they've designated that position and they have agreed to the other terms in the agreement, they would accept the new agreement with the municipal resolution. And then from there, at that point, they've entered into the new process where instead of having a municipal resolution to pass new TE 160s, they could just have that designated position, sign off on the TE 160, send it to PennDOT without having to go through municipal resolution, update that data in TSAMs, make sure everything is in there correctly. And then as part of the new agreement, there's no long appendice list of intersections in the municipality. Any signal that is in TSAMs that is linked to that municipality is considered to be part of that traffic signal maintenance agreement. So as long as the list in TSAMs is up to date, then the traffic signal maintenance agreement itself is up to date, which was a nice stepping stone for this project. This is still an ongoing effort though. We're still waiting to get municipal agreements back from a lot of municipalities. We started collecting these earlier this year. We have roughly, I believe we have roughly 1,200 municipalities that own traffic signals in the state of Pennsylvania, and we have roughly about 100 maintenance agreements back now. So we're constantly collecting those, going through the Office of Chief Counsel, making sure that these agreements are put in place and that we're going by the books on it. We're also going to gather feedback from these in the future, and if there's anything policy related that can be updated or changed based on feedback from our current practices, then we'll use that to update and to maintain our policies moving forward. And then it's also important just to continue to collect and improve data in TSAMs. This is always an ongoing effort in our section, and we have seen an uptick in some data being collected by municipalities after these agreements have been put in place, so that's good. And in the bottom of this page is a little hand-drawn diagram of the kind of thought process when it comes to inputting data into TSAMs for the municipalities. So they'll decide to make modifications. They make those modifications, and as part of the agreement, they'll upload a cabinet picture into TSAMs. So this just makes sure that at the very least we have data in TSAMs that shows what's in the cabinet, and that's important data to have, because at least for those who know what they're looking at, being able to see a recent picture inside of the cabinet really gives you a good idea of what's in there. Some lessons learned from this project and some COVID adaptations that we had to make. Communication is key. I believe this is a lesson learned probably from every project out there, but even though that may be the case, it's still worth noting, it's still worth pointing out. When you're working with so many different stakeholders and so many different people, it's important to make sure you're aware of what everyone's going through, what everyone's thinking, and try to make the best decisions based on input you have. And that's important to keep that communication up between all parties involved. And based on that as well, collecting feedback while you're keeping up that communication. See how people feel about your changes, what makes sense, what doesn't make sense. Anything you can gather, you can definitely use in future updates, future projects, and streamline your own processes as well. As part of the COVID adaptations to this project, we've had to utilize a lot of digital signatures. The form that you see on the right side of your screen here is the TE160 fillable form. Being able to utilize digital signatures for that, especially shrinking down to one page and everything, makes it really nice. Having electronic filing, access in TSAMs, that was definitely a big change for COVID, especially since, as we had noted earlier in the presentation, that 75% of municipalities were still using paper records for their signals. So I'm sure there were a lot of adaptations for a lot of different municipalities, a lot of stakeholders out there when it came to adapting to COVID, and this project is definitely not an exception to that. So I'd like to thank you for taking the time to listen to me talk about trends in traffic signal maintenance. Again, my name is Anthony Chido from BOMO. My information is here on the screen. You can feel free to shoot me an email or call me if you have any questions. I'll also be available whenever the other presentations are done for this session. So thanks again, and I appreciate your time.
Good afternoon. Thank you for joining us for this afternoon's Innovation Day session. My name is Brian Crosley, and I manage the Temporary Traffic Control Unit within BOMO's Highway Safety and Traffic Operations Division. Today I'll be talking about a recent Smart Work Zone demonstration for the Making Smarter Work Zone segment. During last year's Innovations Day, I gave a 101 course on what makes a smart work zone. Since there may have been some who were unable to attend last year's event, I thought it may be best to provide a review of last year's material prior to discussing this year's case study. As defined on the screen, a smart work zone or intelligent work zone can refer to any site-specific configuration of technology that's deployed as part of the work zone devices to help increase safety to workers and road users by providing travel information and efficiency to route motors through or around a work zone or hazard. As defined by the United States Department of Transportation, there are 5 strategies that can be incorporated to make work zones smarter. Those strategies are speed management, traveler information, reducing exposure, managing traffic and performance monitoring. As you might expect, PennDOT has already begun to utilize smart work zone technology that comply with the categories discussed on the previous slide. While some approaches are more visible to the public eye, such as late merge and automated speed enforcement, other approaches, while beneficial, are not as easily recognizable. Queue warning systems, as managed by our Transportation System Management Operations Unit, have been deployed on several key corridors across the Commonwealth, with noticeable success. However, what I would like to discuss today is a recent pilot of smart work zone devices that occurred along a safety corridor project in Lycoming County within PennDOT's Engineering District 3. Earlier this summer, a national manufacturer of work zone devices had requested to share with the department, as well as the Pennsylvania Turnpike Commission, some items from their new product line. These products meet the definition of smart work zone devices because they can provide real-time data and situational awareness within active work zones by communicating via the cloud to the work zone data exchange, as well as third-party vendors such as Waze and Google and others. This critical information can then be communicated to approaching road users via their smartphone devices, as well as directly to the department and the commission through their ATMS platforms and also the PA 511 Traveler Information System. Since the department saw the benefit of deploying one or more of these devices along an active work zone for the purpose of gathering information and providing that solidification of information that we are already receiving through other platforms such as our automated speed enforcement program, but rather than taking the parking lot approach by just simply walking around the devices and kicking the tires, so to speak, we work through a regional supplier that works with the manufacturer and requested to place several of these devices on an agreed project to witness the benefits for future use of these devices. The project that was selected is along the US 220 corridor between Jersey Shore and Williamsport, Pennsylvania. This is in Lycoming County. This project consists of multiple work areas within a 6 to 7 mile stretch that has long-term lane shifts, 1 or 2 long-term lane closures, as well as intermittent short-term lane closures throughout any given point of the week. This route is a north-south commuter route that garners at least 20,000 vehicles per day or more. Of the products available by the manufacturer on the screen are 4 devices that were selected by the department and the commission for the pilot deployment on the project. Through the remaining slides, I will get a little bit more detail of each device and how they were deployed, and then finally I'll wrap up things by discussing some of the successes and challenges that we observed during the use of these devices as part of this pilot program. For the deployment of smart work zone devices, the Bureau of Maintenance of Operation worked with the vendor, the supplier, the District 3 project staff, as well as the contractor to develop the locations where these devices could be deployed. In some instances, existing devices such as arrow boards and speed display signs that were already as part of the project were simply removed and replaced with the smart work zone devices that effectively perform the same functions, but in an enhanced capacity. The first device we're going to talk about are the beginning and ending portable sensor system. This system looks much like a traditional Type B light that is historically installed on signs and channelization devices. However, rather than illuminating, they contain a 4G modem and a GPS system that communicates through the work zone data exchange and through the cloud to push notification to road users related to where a work zone begins and where a work zone might end. This information can be communicated to the road users through Waze and Google applications with the intent to eventually communicate through an autonomous and connected vehicle system. Much like the beginning and end portable sensor system, we also deployed a speed portable sensor system that utilizes, again, a Type B light housing unit, and that can be attached to a MASH compliant solar vertical panel. The sensor system also uses a 4G modem as well as a GPS system to auto-locate and record placement location. It also uses radar technology to collect volume and speed data. Speeds can be recorded for up to 3 lanes of traffic. This system was useful in providing field verification data collecting through the automated speed enforcement program, as this project has been identified as an ideal candidate, which sees regular automated speed enforcement throughout any given week. The Speed Wizard is a combination work zone digital speed limit and speed awareness system. As you can see, it looks much like our standard speed display signs that are deployed among many of our work zones across the Commonwealth, as well as utilized by many safety sections within PennDOT to help enforce lower speed limits in communities and along school areas as well. The lowered speed display adjusts the warning message for drivers based on the speed of the passing motorist. By using a matrix as shown on the left side of this slide, the Speed Wizard's lower display can adjust based on this speed threshold provided by the posted speed limit on the above display. If a passing motorist violates a certain speed threshold, the numeric display can change to read slow down. The device also has capability to collect volume and speed information, which again can be verified against our automated speed enforcement program for its capabilities and verification and accuracy. The last device I want to talk about is the Smart Arrow board. For most people, including the work crews and road users, the Smart Arrow board does not look any different than any standard arrow board. In fact, the work crew installs and activates the Smart Arrow board just like any standard arrow board. However, the Smart Arrow board can report GPS field locations and commute active lane closures to third-party data and government agencies. This is achieved via a modem and a GPS unit that is attached to the back of the arrow board. When activated, the arrow board instantly begins to push information to the work zone data exchange and cloud services reporting its location, its current mode, meaning left lane closed, right lane closed, or caution mode. The Smart Arrow board will also report any changes to its position and which mode it has been changed to, whether it changes from a left merge to a right merge, instantaneously. Project management personnel can receive text alerts to its location and merge mode upon activation, modifications, and deactivation throughout the course of the day. This also helps ensure motorists are seeing the proper work zone messaging as they approach so they can adequately and appropriately adjust their speeds, their driving behavior, and if need be, change lanes prior to getting to the merge point of the work zone. So lastly, successes and challenges. So of the devices that we discussed here this afternoon, on the left side of the slide you see some of the successes. First and foremost, I want to thank District 3 staff as well as the contractor staff for being willing to work with us on this pilot program. I also want to thank the vendors and the suppliers that were involved in this program to make this a reality for us to actually see the capabilities of these devices. All right, so what did we learn from this pilot? In regards to the Smart Arrow board, the contractors seemed very pleased with its functionality, and it would appear that the data we received from it was accurate and it performed in the manner that the manufacturer and the vendor indicated that it would. The start and end work zone sensors, based on the random checks using Waze apps, as well as drive-throughs of the project, also seem to appear that, to us, they worked as intended, and we can certainly see some benefits of using these on other projects moving forward. The speed sensors, again, seemed as if they were providing accurate information, and our analysis team, who also serves as our management team for our automated speed enforcement program that records our speeds, captured through those work zones, basically have reported back that the information they received through those sensors were in line with the data that's collected through the automated speed enforcement program, which is calibrated annually by a third-party vendor. However, on the challenges side, the Speed Wizards, they kind of didn't really look as favorable as maybe we hoped to. For one, the contractor reported that those devices tended to keep shutting off at random times when they weren't anticipating them to. They had to go out and reboot the system and continuously turn them on at various points through the week and sometimes multiple times during the day. It is also, it did not seem as if they were as favorable as getting the driver's attention as we hoped they would be, and sample field reviews of observing traffic behaviors when driving by these devices. Vehicles that may have been going beyond a certain threshold of speed that you would expect would react and slow down did not. And we did not see any real hard braking or anything like that as a result of the change in the messaging and flashing back at the road users. But with that said, it is newer equipment, and like all things, there are probably bugs that can be worked out in that or any of the other devices that we experimented with, as well as they performed for us. There's certainly always room for improvement, and we understand that. So by no means does this mean we are completely turned away from using that device or any other device. Those were just our observations, and we certainly look to work on building on these to make work zones safer and smarter moving forward. So with that, I'd like to close out the session by thanking you for taking the time to listen to my presentation and for selecting this as part of your afternoon session for day one of Innovations Day. At this time, I'm going to hand things back over to the Innovations team, where I believe that we're going to pause for some questions and answers at some point during this presentation. So again, thank you for listening, and I hope you have a great week at Innovations Day. Thank you.
Hello, I'm Jeff Bucher. I'm Acting Section Chief for the Highway Design and Technology section in the Bureau of Project Delivery, and I'm also the statewide roundabout coordinator. I'm going to give you a brief overview of where the department stands regarding innovative intersections and interchanges, primarily focused on roundabouts and diverging diamond interchanges. I'd like to remind everybody that we do have an intersection control evaluation policy. It was issued back in September of 2018 as Appendix AI to Design Manual 1X. It covers the intersections listed here. The green ones are more of the innovative intersections, and the black text are the standard ones that most people are used to. The associated software spreadsheets available on the traffic signal portal at the link shown. Under the highlights of why we're building roundabouts throughout Pennsylvania, as they are nationally, the primary reason are the safety benefits. Every year we do a study of the roundabouts that have at least 3 years of before and after crash data and that are previously stop or signal controlled intersections. Through the end of 2020, we had 26 roundabouts that met that criteria. And the study showed that we had 100% reduction in fatalities, 67% reduction in injuries, and a 22% reduction in crashes. The national data that's shown there is quite old, but I don't have anything more current to show in comparison, unfortunately. So as you can see, from a safety standpoint, roundabouts are performing quite well throughout Pennsylvania in comparison to the previous type of intersection. But you have to keep in mind that there are other benefits to roundabouts. They can be up to 30% more efficient than signalized intersections during peak times, and you have pretty much no delay during off-peak times. They also reduce emissions because of the nature of the continuous flow. They have significant traffic calming benefits because they geometrically restrict the speeds of vehicles. And there's beautification aspects for gateways to communities and so forth. As far as roundabouts being implemented throughout the state, we built our first roundabout in 2005. And we have a total of 62 roundabouts currently on state routes, 77 overall within the state, 20 more in construction that aren't open to traffic, and another 30 or more than 30 in design. Other innovative intersections, as from the previously shown list, that should be considered for significant intersection upgrades: median U-turns, restricted crossing U-turns, displaced left turns, continuous green Ts, and quadrant roadways. The Federal Highway Administration has a guide for median U-turns, restricted crossing U-turns, and displaced left turns, which you can find on their website. As for diverging diamond interchanges, similar to the other innovative intersections, the primary idea is to get the high left turning traffic volumes to turn while the through traffic in the opposing direction continues to travel to avoid excessive delays. And they also improve safety by having fewer conflict points than typical signalized intersections. And frequently they use up less right of way than other interchange types. DDIs built throughout Pennsylvania and under design. Our first one was in Washington County on I-70 at SR19, which opened back in 2016 and is performing quite well. Two recently opened in District 8, one at I-83 Exit 4, and the other at SR322 and SR222 in Lancaster County, which you'll be hearing a presentation on here briefly. And under design, there are several in District 5, and the image shown here is of the one proposed in Westmoreland County in District 12 that is to go to construction next summer. Here's some useful links. The first one is the link to the Roundabout website within the PennDOT website. The second one is the link to the traffic signal portal, which I mentioned earlier. And then a couple links to the Federal Highway Safety website. The first one will go over roundabouts, and the second one will cover various other intersection types, including displaced left turns and median U-turn intersections. And that concludes my presentation. Thank you.
Good afternoon. My name is Brett Abrahamson. My colleague Greg Frisbee and I will be presenting the SR322 and SR222 Diverging Diamond Interchange project today. To provide some background on our involvement, I was the senior highway engineer for the project and Greg was our senior traffic engineer. With quick introductions out of the way, let's get started. We wanted to start off by mentioning the team that worked hard to produce this successful project. Our project team was led by Dave Fertangeli of PennDOT District 8, who was unfortunately unable to join us for this presentation. Barb Karsak-Anderson led the PennDOT construction team. Our consultant design team was led by WRA, with assistance from Stantec Consulting, Wallace Montgomery, Skelly & Loy, Susquehanna Civil, and SAM. Finally, the contractor for the project was JD Ekman, with CM High and Signal Control Products as key subcontractors. Now, let's touch on the project history and project location. The project is located at the existing SR322 and SR222 interchange, just east of Ephrata in Lancaster County, District 8. The project was initiated in July 2013 as part of a road safety audit, which recommended an interchange alternative analysis be performed. In December 2013, a DDI feasibility study was performed that determined a DDI would be a feasible solution and provide safety and operational improvements. In December 2016, our team completed a comprehensive alternative analysis study. Following the study, PennDOT selected the DDI as the preferred alternative. From there, the project spent a little over 2 years in design, and the construction NTP was issued in November of 2019. In May of this year, the DDI opened to traffic, and the project is now substantially complete. The primary purpose of the project was to improve safety. After reviewing the crash history at the interchange, we felt that the best way to accomplish our goal of improving safety was to 1. Reduce the number of conflict points within the interchange, which naturally reduces the opportunity for accidents to occur. 2. We wanted to eliminate the SR322 left turn and opposing through movement conflicts through the interchange. The existing crash data indicated that this conflict resulted in 43% of the angle crashes and 43% of the rear end crashes within the interchange. 3. We wanted to reduce the number of and severity of future crashes. The existing crash data indicated that 46% of the crashes resulted in injuries. While our primary purpose and need was safety, we also identified 2 other project objectives. We wanted to improve safety, but we didn't want that to come at the cost of degrading traffic operations or multimodal transportation. For traffic operations, we wanted to reduce queuing on SR322 as well as the off-ramps from SR222. As for the multimodal operations, we recognize the importance of ensuring that pedestrians, bikes, and unique to this particular project, horse and buggies, were accommodated due to the significant presence of the Plainset community in the area. After diving into the project, we developed a more specific list of issues that we wanted the project to address. With the goal of the project being to improve safety, we wanted to address the high number of reported injury crashes due to the frequent angle collisions at the SR 322 intersection with Sheetz Walmart, as well as for the unprotected SR 322 eastbound to SR 222 northbound movement due to the lack of a traffic signal. From a traffic operations perspective, there were frequent backups on SR 322 eastbound at the Sheetz Walmart intersection. Short left turn lanes cause traffic to routinely back up into SR 322 travel lanes in both directions, which also becomes a safety issue. On the SR 222 off-ramps, a lack of a formal right turn lane leads drivers to use shoulders, and traffic routinely backs up on the ramps during peak periods. In addition, we wanted to address the missing sidewalk connection under the SR 222 bridges and also improve the substandard bridge clearance. Our team initially investigated 5 alternatives before settling on 3 alternatives for further development. After comparing the 3 alternatives, it was decided that the DDI met the primary and secondary purpose and needs, and also provided a 13-to-1 benefit to cost ratio, which was the best of the 3 alternatives. The major benefits of the DDI compared to the other alternatives is that it improves safety by reducing the number of conflict points from 28 to 14 as compared to the current diamond interchange. It reduces travel delay by utilizing 2-phase traffic signals with short cycle lengths at the ramp signals. It increases the capacity of the turning movements on and off the ramps. It utilizes the existing SR 222 bridges and generally maintains the same footprint, thus requiring minimal additional right-of-way. Finally, it also accommodates multimodal transportation, which, given the presence of the Plainset community, was a critical component to the project. We wanted to take a minute to quickly explain how the DDI works for those that may not be familiar with how one functions. The graphic on this slide shows how all of the movements are made in a DDI. The DDI is unique from a standard diamond interchange in that traffic on the minor road, which in this case would be SR 322 running left and right on your screen, temporarily crosses to the left side of the road via signalized intersections on either side of the major road, which in this case is SR 222. This allows for direct left turns to and from the SR 222 ramps without crossing conflicts with SR 322 traffic. Traffic on SR 322 then crosses back to the right side of the road at the far side of the signalized intersection. Now let me get into some of the nuts and bolts of the geometric design considerations for the project. Since this project is at the interchange of 2 major state routes, we had to ensure that larger design vehicles, such as WB67s, could make all movements and run concurrently with other vehicles. Similar to roundabout design, this requirement was often at odds with the necessary curvature of the roadways, which required careful placement of curb lines. Secondly, and possibly most critical to a DDI's geometry, is the design of the crossover intersections. A 45-degree crossover angle was selected, which is the recommended minimum value to deter wrong-way maneuvers. Due to the location of the nearby Sheetz Walmart and Hanstown Road intersections, the tangent length between crossovers had to be kept to a minimum, which in this case was between 120 and 130 feet. This provided greater and more desirable spacing from the adjacent intersections, and fortunately, the wider resulting cross-section could be supported beneath the existing SR 222 bridges. A review of natural vehicle paths through the crossover intersections was performed to evaluate the potential for path overlap. Finally, concrete glare screen was strategically placed within the median between crossovers and on the right side of the near side approaches to create a blinder effect and impede the view of opposing traffic as drivers cross over to the left side of the roadway. Ramp design was also critical to properly align with the crossover intersections, and a new SR 222 northbound ramp spur to SR 322 westbound was added, which provided a more direct route for that movement and improved operations at the Hanstown Road signal. The final design element I wanted to mention is the vertical clearance under the SR 222 bridges. The profile along SR 322 was set to generally match existing. However, the profile was reduced and the pavement subsequently reconstructed to drop the profile by approximately 9 inches under the bridges. This improvement to the vertical clearance allowed for the clearance posting of the structure to be removed.
Thanks, Brett. In addition to unique geometric design considerations of the DDI design, we wanted to highlight some traffic design elements of the project. Due to the closer proximity of the DDI crossover intersections, progression between both crossovers is critical to operations. Therefore, one traffic signal controller was utilized to control both crossovers. Traffic signal timings emphasize queue management and progression for critical interchange movements. Other traffic signal design elements included the installation of radar detection and emergency preemption. Left turn phasing at adjacent signals utilized flashing yellow arrow indications to maximize both safety and operations. The project also included the installation of a CCTV at the interchange and took an innovative approach to backhaul communications by utilizing a shared connection for the CCTV and traffic signal system that eliminates long-term service costs for the municipality. Lighting was also installed along 322 and at critical ramp decision points. Enhanced signing, including overhead guide sign structures along 322, were installed and recessed pavement markings were provided for improved long-term durability. As mentioned previously, ensuring appropriate multimodal accommodations was a priority of the project, especially due to the large Plains Sec community that utilizes 322. The project improved pedestrian connectivity and accessibility along 322 through the project limits by completing a missing sidewalk connection and installing and upgrading pedestrian facilities to meet ADA guidelines. 8-foot wide shoulders were provided throughout the project area for bicyclists and horse and buggy traffic. Radar detection zones were included in shoulders to detect horse and buggies so the traffic signals could work correctly during periods when vehicular traffic may be lower. Because the DDI is a relatively new interchange configuration in the United States and there was only one in Pennsylvania at the time we were in design, educating the public on how a DDI works was critical. We held several meetings with public officials, the general public, and special purpose meetings with leaders from the Plains Sec community. We utilized several diagrams showing how the DDI works, developed a brochure shown on the slide, and utilized an instructional video on how to navigate a DDI. Based on the feedback received following the outreach events, attendees felt more comfortable with the DDI as the correct solution. Because the Plains Sec community is traveling through the DDI using non-vehicular modes of travel, we met with them specifically to show them how we envision pedestrians, bicyclists, and horse and buggy traffic navigating the DDI. We wanted to make sure that the facilities being designed would be used as we intended. The Plains Sec community agreed with all of the project's provisions and were very appreciative to be involved in the design process. We wanted to share a few items that could be considered with future DDI projects. The first relates to having lighting installed in advance of the DDI switchover. Our schedule provided sufficient time to allow for the installation of the permanent lights prior to the DDI switchover. However, excessive pole fabrication delays and the accelerated construction due to COVID-19 presented an unexpected challenge. In response, we performed a photometric analysis to determine a low-cost temporary solution to ensure the interchange was lit for the traffic switch without delaying the overall construction schedule. One of the lessons learned from the construction of Pennsylvania's first DDI was to utilize a weekend detour to switch into the DDI operations, which was successfully done for this project. Lastly, we wanted to mention work restrictions. Around mid-morning on the opening day of the switch to the DDI configuration, the contractor was working at multiple locations around the project. This caused driver confusion as drivers were attempting to utilize a new, unfamiliar traffic configuration for the first time. We recommend limiting work at the site for the first week following the traffic switch, and especially not allowing any lane closures to allow for drivers to successfully navigate the DDI a few times. The DDI was open to traffic on May 17, 2021. As expected, public reactions were mixed as the traveling public utilized the DDI for what was likely their first time in an interchange of this type. Observations and minimal complaints over the next few days indicated that the public was navigating the DDI successfully. Fast forward 4 months to August of this year, and overall the reviews seem positive, with drivers having become more familiar with the interchange. Although it is too early to tell the long-term safety performance, left turn and angle crash types appear to be minimized. That concludes our presentation. We appreciate the opportunity to present PennDOT District 8's SR 322-222 Diverging Diamond Interchange project. Thank you and have a good day.
Good afternoon. My name is Scott Benedict. I'm a Senior Traffic Control Specialist in PennDOT's Traffic Systems and Performance Unit. More specifically, I am the Project Manager for PennDOT's TSMO Performance Program. I'm going to be presenting on improving performance within traffic operations and how we are accomplishing that with our TSMO Performance Program and the Traffic Operations Analytics Platform. When we first began looking at the performance of traffic operations several years ago, there was a problem. Decisions about how to best operate our roadways and manage traffic were largely based on anecdotal experiences and presumed best practices. Our leadership was concerned that we were putting so much money into traffic operations, but we lacked the ability to really understand the effectiveness of our efforts, which made it difficult to justify changes and improvements. The goal was to move from this state of play to one where operational decisions making was driven by data and to develop career metrics that could be used to evaluate and communicate program progress and improvements. As a result, the PennDOT TSMO Performance Program was created, and one of the first efforts of that program was the development of our Traffic Operations Analytics, or TOA for short, platform. Our goal in creating the TOA platform was to bring together a variety of data sources that would better help us understand where crashes and other traffic incidents were occurring and how well we were responding to them. The initial implementation of TOA brought together data from both PennDOT and third-party sources. The PennDOT sources were our crash record system, which has information on all reportable crashes that occur throughout the state, as well as our road condition reporting system, RCRS, which is our real-time database of all incidents and roadwork that our traffic management personnel are aware of on state roads. The third-party data included crowdsourced incident data from Waze and traffic probe speed data from INRIX. These data sets were correlated to give us a much more complete and clear picture of where incidents were occurring on our roadways. Once the data was correlated, Microsoft Power BI was used as the front end to create reports and visualizations that could be in turn used to turn the data into actionable information. TOA has since expanded to include a number of additional department sources as seen on the slide, such as our weather station data, our maintenance database, our ITS locations, our DMS message histories. That's allowed us to begin to continue to perform additional analysis across a wider variety of areas. All told, we now have a massive database in excess of 30 terabytes, and that's expanding daily. Armed with the TOA platform, the TSMO Performance Program began issuing TSMO Performance Reports in February of 2018. The goal of these reports was to provide traffic operations personnel and other interested leadership and stakeholders, both external and internal, with an understanding of how traffic operations were performing and where things could be improved. The initial performance report was focused on our traffic management centers and their situational awareness of reportable crashes, but the 5 reports that have been issued over the years have covered a variety of topics. All of our performance reports are available for viewing on PennDOT's TSMO page, which can be found at the provided link. But you don't have to remember the link. Just search for PennDOT TSMO and you will quickly be able to find our page. To date, the work of the TSMO Performance Program has primarily focused our analysis on PennDOT's core roadway network, which is depicted here. The core roadway network is essentially PennDOT's network of major freeways and limited access routes, as well as a few key arterial sections that were needed to properly connect up the network so that we have a full network. As you can see from the slide, traffic operations are managed regionally at PennDOT, as depicted by the different colors that you see on the map. Each region has a 24/7 regional traffic management center, and we also have a 24/7 statewide traffic management center that provides oversight and coordination. You can see from the pie chart on the right a breakdown of how much core network mileage is in each region. The core network consists of the roads in the states that are most important for moving people and goods across the state. Additionally, they tend to be the roads where we have the best data available to do performance analysis. So these are the roads that we focus on. One of the goals of the TSMO Performance Program is improving our response to unplanned traffic incidents. This can be achieved by better responses after incidents occur, but also by identifying conditions that cause those incidents to occur and finding ways to prevent them from happening in the first place. One of the first metrics that the TOA platform improved our ability to calculate and to understand was incident clearance times. Incident clearance time is defined as the time from when an incident occurs until the last responder has left the scene and traffic is completely clear. Bringing in crowdsourced incident data from Waze and traffic speed data from INRIX has allowed us to get a much more accurate picture of when incidents actually begin, which then also allows us to have a much more accurate picture of how long it takes them to be cleared. This information can then be provided to our TMCs and our other incident management partners for evaluation of how our response and our clearance times can be improved. We provided data on our core network at the county level and also on an interstate county level as seen here, but our TOA has also recently been updated to allow us to even get down to the municipality level. Bringing in data from our road weather information system has also allowed us to evaluate and identify the impact that adverse roadway and weather conditions have on crashes and the point at which travel becomes more dangerous. You can see the conditions that we've identified here and their impact on the likelihood of crashes for both commercial and non-commercial vehicles. Since ROS data is provided in real time, we're in the process of implementing automated alerts to our traffic management personnel for this winter so that they can provide messaging using our message signs and other tools for informing the public that will alert travelers to these hazardous conditions before the crashes occur, hopefully encouraging them to slow down, to take different routes, and then thus prevent crashes from occurring in the first place. The longer term goal is for this kind of messaging and alerts to the public to be completely automated. We've also done an analysis on the incidents that cause full roadway closures on our core network during these hazardous conditions, looking at both how long the closure lasts and the incident influence time. Incident influence time is defined as the time from when the incident occurs until traffic speeds have returned to historical norms. As you can see, the majority of these closures involve commercial vehicles, and the closures that involve commercial vehicles have significantly longer impact on traffic, both in terms of how long the road is actually closed and in terms of how long it takes traffic to get back to normal after the incident is cleared. This information is providing support and justification for the commercial vehicle restrictions that we place on our core roadway network during winter storms in order to help with traffic operations and keep the roads moving during those storms. In addition to improving incident response, another goal of the TSMO performance program is to help operations and planning personnel better understand the nature of congestion on the roads that they're responsible for so that they can better design solutions to address that congestion. To that end, the TSMO performance program developed and released in early 2020 a first of its kind congestion pie chart, which was based on real data from the data sources that we have, and it was developed for our core roadway network. The pie chart tool breaks down congestion by its primary cause, as seen here. Causes that we have identified for use in this pie chart are roadwork, crashes, both major and minor, as well as other traffic incidents, weather, recurring congestion, rubbernecking from traffic events on the other side of the road, and then congestion for which we are unable to identify a cause with our available data, which is a relatively small percentage of the total. The tool provides the ability to look at congestion for a variety of geographies, as seen here. I provided a chart for the entire core network in Pennsylvania, and then you can also go down and see the metro Pittsburgh area for our core road network, and then you can even look at a specific route, I-376, in a specific county, Allegheny County, right in the Pittsburgh area. As of this year, the tool can also go down to the municipality level. The original pie chart tool was released with 2018 data, and we've updated it annually ever since, 2020 being the most recent year available, and that's the data that I've supplied here. The congestion pie chart has been utilized within our department for the development of our regional operations plans, as well as other planning efforts, and is being reviewed by operational personnel so they have a better understanding of congestion in their region. Like every other area of life, traffic and traffic operations have seen a significant impact as a result of the COVID-19 pandemic, which began impacting PA in a significant way in March of 2020. Due to the various mitigation efforts, traffic volumes on the core roadway network fell dramatically in the spring of 2020, and while they have recovered throughout the summer and the fall and into this year, they remain roughly 5% lower than pre-pandemic levels due to increased teleworking and other factors impacted by the pandemic. Less people traveling obviously means less congestion, and while we did not see a significant shift in the breakdown of congestion types, the congestion pie chart tool did allow us to see the overall drop in congestion as depicted here with this stacked bar chart. You can see a significant decrease in the amount of total congestion from 2019 to 2020, and that total impact of congestion on the core road network fell by 73% in 2020. Another tool that we have developed recently in order to help our operations personnel and other interested parties to be able to better understand the congestion in their area is our congestion calendar tool, which is seen here. This tool provides a clear visual picture of congestion on a road or a set of roads for each day of the year so that you can quickly identify when your trouble days might be and be able to analyze potential causes and solutions. To that end, the tool also includes the congestion pie chart data for the days where we have it calculated, so that you can, if you click on a specific day, you can see quickly what was causing the congestion on that day. Like our other tools, this one can provide data down to the route, county, and even the municipality. This concludes my presentation. I would like to thank you for your time. If you have any questions about what I've presented here, I will be available for questions at the end of the session, or you can reach out to me directly afterwards via the contact information I provided here. Thank you again.